It's time for problem 2. Now, problem 2 actually starts out very similar to problem 1, so let's think about that one again. Here is an object sitting on the ground. I'm going to push the object at an angle. I can take that force I'm pushing at an angle and break it into these two pieces. So really, instead of thinking of the object being pushed down at an angle, I can really pretend that I'm pushing down and over at the same time. This makes the problem a lot easier to solve. And it's basically the same idea. Well, now let's do this again, but think about our skateboarder. Could I take our skateboarder sitting on the ground and push him at an angle? If so, then I can say that I'm pushing him down and over at the same time. But our skateboarder isn't sitting on the flat ground. He is on a hill. And the thing that is pulling him the most, or the only thing pulling him, is gravity. So this line here really represents the force of gravity. But gravity doesn't really pull him down. It's really pulling him into the hill and down the hill at the same time. We can break this force into two pieces just as we would any other. Now I know what you're thinking. Why take gravity, which is in the convenient y direction, and break it into weird directions? Well, the reason for this is gravity is no longer in a convenient direction. This hill is at an angle. It would be nice to do all of our work at this same angle. If we turn it back to flat, we work in the x and y plane because that's where most of our problems live. Since this problem lives on an angle, why don't we turn our solution to be on that angle? Now to simplify it, let's flatten it out again and do a little bit of work to figure out how we can solve this. First of all, I said this hill is at a particular angle, theta. Now if I make this into a big triangle, where that is 90 degrees, I find out that this angle up here, I'm going to call this phi, is actually 90 minus theta. 90 minus theta. Now, if this is 90 minus theta, and this angle here is 90 degrees, the interior angle here actually becomes theta. Thus, this angle is the same as this angle. If you don't believe me, ask your geometry teacher. Now, if we can move on from that, we can turn our problem back and just focus in on this one triangle. I know FG. That's something that's pretty easy to find. And I know this angle. Well, I can break FG into two pieces. This side and this side. Where over here, since I am opposite the angle, the piece of FG I get is equal to FG times sine of my angle. Since this force is next to the angle, it is equal to Fg times the cosine of my angle. Now, that's all well and good, but we need names for these. Now, in our actual problem on the hill, Fg is going in the y direction. We have decided to not work in the x and y direction, so we should give new names for these. Since x and y don't really make sense, let's name them in regards to the hill. This force is coming perpendicularly out of the hill, so let's call it F perpendicular, where that sign means perpendicular. This line is going parallel to the hill. Let's call it F parallel. Now, I can do a little bit of work with my skateboarder. In fact, I can take him completely off of here and draw a new problem. where here's my skateboarder, who is being exerted a parallel force and a perpendicular force. However, the skateboarder rolls down the hill in the parallel direction. He doesn't go into the hill. That's because the hill pushes back on him with normal force. In this situation, normal force is equal and opposite perpendicular force. Meanwhile, parallel force has nothing to cancel it out, so it makes the skateboarder accelerate down the hill. Since you know how long he's on the ramp, and you know his force, or the force pushing him, and you know his mass, you should be able to tell me his acceleration. If you know his acceleration, you should be able to find his final speed. That's all your help for the second problem. I hope that you found this useful.